I'd like to thank the organizers for the invitation to this beautiful place, and I apologize since the topic of my talk has nothing to do with symplectic or Poisson geometry. In fact, I remember 13 years ago there was a conference in 2006 when also I planned to give a talk not related to the theme of the conference, and I felt uneasy about it, and indeed the talk was cancelled, and your talk was cancelled too as a morning session chairman, and instead Witten gave an 8-hour long talk about electromagnetic duality with Kapustin. Unfortunately, this didn't work this time. So let's start with first part. So these are all fancy notions, but indeed the Coulomb branch we consider is the very simplest one. So it's a K-theoretic Coulomb branch, but it is just the equivariant K-theory almost there. So it corresponds just to one vertex quiver, A1 quiver. And then it is equipped with some convolution operation, and it is a commutative algebra. And its spectrum is isomorphic to so-called Zastava space for SL2 of degree n. And again, this is some fancy name, but in reality this is just the space of pairs of polynomials, Q of z and R of z. So Q of z is degree n polynomial. And R of z is a degree less than n polynomial. And there are two open conditions. First, that Q naught does not vanish, and second, that Q and R are relatively prime. That is the resultant of Q and R is not zero. And maybe because of this condition, this is called multiplicative or trigonometric Zastava. Okay, so this is just an open subspace of two n-dimensional affine space. And this isomorphism is very explicit. Namely, well, let me introduce certain auxiliary coordinates on this side, and then I will say what will they go to on the Grassmannian side. So we take R of z over Q of z, and we develop it at infinity. So it's the sum of there's infinite Taylor series in the inverse, and now we form a Hankel matrix like this. And so on. And then we take some minors of this matrix, namely like this. And these are delta 1, delta 2, delta 3, and so on. And also like that, just the shifted ones. And so on. So this will be delta 1 prime, delta 2 prime, delta 3 prime, and so on. And these will be our coordinates. And on the Grassmannian side, we consider the fundamental, minuscule fundamental Schubert varieties. Just the moduli space of sublattices in the standard one. Of codimension K, which are killed by Z, and then there is determinant line bundle. So, well, in fact, this is isomorphic just to the Grassmannian, the usual finite-dimensional Grassmannian of k-dimensional planes and n-dimensional space, and so it carries the line bundles O of S. So the line bundle O of S on this guy will be, its class in the K group will be denoted by PKS. Okay, and finally PK0 will go to delta K, and K1 will go to delta prime K, as long as K is between 0 and n, and here K is between 0 and n minus 1. And
0, 1. So you're saying 0, but you're writing 1.
Oh, sorry, I should say 1. Mm-hmm. And also the last one, N1 will go to delta prime n over delta n. Okay. By the way, delta n is just this result here. So it's invertible. Okay. So this is the isomorphism. And there is a theorem due to Wiechmann, Shapira, and Weinstein. That this algebra of functions on Zastava space has a cluster algebra structure with the exchange graph given by this. And there are two frozen variables in the end. And here p n minus 1, 0, p n minus 1, 1, and so on. Okay. So now let me maybe explain a little bit why does it happen. Yes?
Why do you only consider x equals 0 and x equals 1?
Well, it's enough. I mean, this algebra is generated by these guys, and as well as this algebra is generated by those minors, and they correspond in this way.
Could you write PKS2 also as some minors, like some more shifted minors?
Probably I don't remember. I don't know. Sorry.
And is there a relation between the G equivariant K theory of a point and Q?
Yes, certainly. The coefficients of Q are just elementary symmetric polynomials in the equivariant K theory of a point with respect to GLN. Yes.
Which in some sense answers David's question.
Why?
Because that tells you how to multiply by elements coming from K theory of a point.
But it doesn't give you S equals 2, does it?
It does, because you can put any representation there, and you can put trivial bundle here with the current structure coming from some representation.
Yes.
Then you can filter this with.
Well, in principle, yes, but explicit formula in terms of minors, I don't remember. Okay. So, well, there is the following fact that this Zastava space is isomorphic to the certain open Richardson variety in the affine flag variety of SL2 or SL2 hat. Maybe let me put hat here. Namely, the one which is intersection of two opposite Schubert cells. One goes from S1, another from S1. Let me explain what I mean. So the torus fixed points of the affine flag variety are numbered by the affine while group, and now the affine while group of SL2 hat is generated by two simple reflections, S0 and S1, and these are the fixed points in question. So now I take the orbit with respect to n minus the radical of opposite Ivahori of S1 and intersect it with the orbit of n plus of S1, 0, S1 to the power n. And this is my open Richardson variety. And there is some natural isomorphism with this Zastava space. Now these open Richardson varieties were studied a lot by the from the very beginning in the framework of cluster algebras, and they usually do carry some cluster structure. The initial cluster in the favorable situations consists just of some generalized minors, and this is the case here. So namely, we associate to the pair Q and R, like here. It's scattering matrix. S, which is just z to the power negative n Q. z to the power negative n r, and then some extra column. So here f again starts from z to the power n, and the degree of d is less than n again, and the determinant of this matrix is required to be 1. And then it's easy to see that there is a unique way to find such d and f, so that this condition is satisfied. So the scattering matrix is uniquely defined by this point of Zastava space. And moreover, it lies in this negative unipotent radical. So S lies in n minus. And then we just take the generalized minors delta S1 omega naught, S1 S0 S1 to the power n omega naught, and this will be delta, sorry, to the power k. This will be delta k from here, and okay, and this is a theorem of Galina Dobrovolska. Okay. Okay. So this cluster algebra for Zastava business is just a very particular case of the general theory due to Leclerc, maybe in the utmost generality. Yes.
What do you mean by omega naught and omega 1?
These are just omega naught and omega 1 are fundamental weights of SL2 hat. Okay. So, well, these are functions on the corresponding group, in particular on n minus, and now we embedded Zastava into n minus via scattering matrix. So these are functions on Zastava, and these correspond to these minors.
This matrix also lies in n plus, right?
That's true. Only no. N plus should have positive powers of z, right? These are opposite of ours. Yeah. So
it lies in some other
in the toy version of n. Yeah. Right. Okay. So there we are. But let me only mention that that our Zastava space was an open subvariety in the affine two-dimensional space, and this is not a coincidence. Namely, as it usually happens, the Schubert varieties they are simultaneously they may be identified with certain subgroups of nilpotent group, or with the quotients by the stabilizer subgroup. And this subspace is also a certain quotient of the unipotent group n minus, and in this way the functions on Zastava space they embed into functions on n minus, but maybe somewhat localized. Okay, and it will be important in what follows.
Sorry.
Yes?
What were these generalized minors again?
These minors?
Yeah.
Well, just take some extremal vector of this weight,
Yeah.
take some extremal vector of this weight, then we take the scalar product of one vector and g times another vector. Just the matrix elements.
In the second, this is omega 1, omega 0.
Oh, sorry, it's omega 1. Yes, thank you. Thank you. Okay. So now let's go to quantization, because you see in the title there is this extra C star equivariance, loop rotation equivariance. And so we started with equivariance without loop rotation, and then our algebra was commutative. But now let's recall this extra parameter. So we'll first quantize this. And we will need UQ minus of SL2 hat. Well, this is just an algebra over the field of rational functions in Q of with two generators, F0 and F1, and with the two relations, Fi cube Fj minus Q squared plus Q inverse squared, Fi squared Fj Fi plus Q squared plus Q inverse Fi Fj Fi squared minus Fj Fi cubed. Okay. And well, it carries Lustig's perfect pairing, where the pairing of Fi and Fj is y minus Q inverse squared inverse delta ij. And then let me consider a subalgebra there, which will be related to this two-n-dimensional subalgebra, like here. So UN will be generated by the root generators in degrees, well, beta 1 and so on, beta 2n. So beta 1 will be just negative alpha 0, and beta 2 will be negative S0 alpha 1, and beta 3 will be negative S1 S0, S0 S1 alpha 0, and so on, so that beta k is just negative k alpha 0, negative k minus 1 alpha 1. Okay, and the root generators are obtained from these simple root generators by applying Lustig's symmetries, break group action. And this subalgebra I wanted is generated just by those guys. Okay. So now we have a PBW basis of UN, just for a sequence of positive integers. I get the product of these generators. Maybe I should name them somehow. Generators F beta I, like this. F of A is just the product F of beta 1 to the power A1, and so on. Beta 2n to the power A2n. Okay, and now because of this perfect pairing, we have an isomorphism to the dual, restricted dual algebra. Okay, and in particular, it takes the subalgebra UN into subalgebra AN here. And now this subalgebra also has some natural basis, namely the dual PBW basis. Pardon me?
What is UN quantizing?
Well, I didn't introduce integral form yet, but I can now. I will do in a minute, and then it will come to quantize the universal developing algebra of certain subalgebra of this n minus. But the dual one will quantize the algebra of functions, the commutative one.
On some subgroup.
Yes, yes. So
This map's not an algebra map. It's
Uh,
not an algebra map.
they are. Why? They are.
No, so, wait.
Well, because Lucy's pairing is.
Self-dual.
Yes, it's self-dual. The Lucy's pairing is somehow extended with co-multiplication. So by the very construction, it's a homomorphism algebras. I only gave it on the generators, but then extended to everything via co-multiplication. So the dual maybe, in fact, I made a mistake here. These should be divided powers. Okay, and in the dual PBW basis, there is no divided powers, so F star of A is 1 minus Q negative squared times the product F of beta 1 of beta n to the power a1, power an, and now there is no divided powers. Okay, and they are really dual with respect to this loose-stick pairing. Okay, and in fact they're both orthogonal, not orthonormal but orthogonal. Okay, and now I can introduce the corresponding integral forms. Subalgebras over the Laurent polynomials just spanned by the PBW or dual PBW base. Okay, so let me note them by script letters, UN in UN and AN in AN. Okay. In fact, maybe let me also extend scalars to square root of Q for the future application. And now I repeat that this algebra at Q equals 1 becomes some universal enveloping subalgebra. And this algebra at Q equals 1 becomes just the function on some quotient group. Like this, so this becomes commutative when Q is 1. Okay. Now, the last thing I need here is the canonical basis as opposed to PBW basis. I have a very stupid involution which takes Fi to Fi and Q to Q inverse, so there is an evolution, bar evolution from UN to UN, and a dual involution from AN to AN. And now the canonical basis, or maybe let me give the dual canonical basis, B, is characterized by two properties. First, that B star of A is the same thing, so it's invariant with respect to this bar involution. And second is that B star of A is F star of A plus the sum of other PBW, dual PBW elements, but with coefficients, well, in fact, the integral coefficients like this. Okay, and this is called positivity property. Well, maybe it should be called negativity property, just because all these degrees are the same sign. The degrees are all negative. Okay, so it exists and is unique, and we will. Well, this is the basis of the title. Okay, so now let me. Pardon me? Pardon me? Here? No, it's not, this is Z. The positivity only refers to the degrees of Q. Okay, so now let me mention now the theorem of Leclerc that this A n is a quantum cluster algebra, and the initial cluster consists of a certain quantum generalized minors in particular the last two variables x2n minus 1 is just some generalized minor s0 s1 to the power n omega naught and x2n is another generalized minor s0 s1 to the power n omega 1 and these two are frozen variables again.
What's the relation between AN and this?
Pardon me?
Is AN related to this open Richardson that you heard earlier?
Oh, yes, absolutely. It's just quantization of this open Richardson, yes.
Here you said it's the quantization of this.
Pardon me?
So this n prime is like, I think,
It's some double quotient of the negative unipotent subgroup, which is okay. So x2n minus 1 and x2n lie in the Q center of AN. They are frozen variables, and we can consider localized algebra. Like this, and it will have also a dual canonical basis. Say B tilde star of A, and now A is a sequence of integers, but the two last one can be negative, and we just multiply by some powers of these two. Okay, and maybe it's by some power of Q. Okay.
Is there a reason why sometimes capital B and sometimes lowercase b? Is it the same?
I don't know. So this capital case means the collection of all basis elements, and this is a particular basic element, and so the whole base is obtained by taking the whole dual canonical basis and multiplying by negative powers.
But there's also an A.
Sorry, yes.
All ones, if there's an A.
Sorry, yes. Thank you. Okay, and anything else? Okay, and now there is a theorem due to Sabin Cautis and Harold Williams. That there is a isomorphism phi from this localized quantum cluster algebra. In fact, it is called quantum unipotent cell. Maybe I should write it somewhere. Yeah, so this is called quantum unipotent cell. Okay, and it is isomorphic to our quantized Coulomb range K-theoretic. Okay, and under this isomorphism, the generators, the dual generators f over b beta k go to p 1 n plus 1 minus k, and maybe multiplied by square root of q. And that's why I needed this extension scalars to square root of q. And in fact, here I also need to extend scalars. Okay. Okay. And now let me go to the last part of the title, the intersection cohomology basis.
So what
Yes.
does it mean, this tensor you just wrote down?
So I just extend scalars to
Tensor K by that.
yeah, so I take K theory. It is a module over the equivariant K theory of the point. Well, it has symmetric polynomials in n variables here, symmetric Laurent polynomials, and also has some generator for the loop rotation equivariant K theory, which is called Q. Okay, and now I just extend scalars to square root of Q. I may forget this, but this exact formula involves square root of Q. So to be on the safe side, I should extend scalars to square root of Q.
Do you also show that the cluster of monomials are dual canonical-based elements?
Say again, please.
Do they show that the cluster monomials are elements of dual
I see. Yes, this is always true, yes. And they also show that the Cautis Williams show that the cluster monomials go to certain IC classes. Mm-hmm.
Wouldn't these localized guys go to this xn, the ones that are inverting?
So x to n minus 1 goes to just the determinant character of GLN sitting at the point 0, yeah, and x to n goes to the what is called p to n 0. Pn 0. So it is the last fundamental Schubert variety, which is just a point. Okay, and then I just take trivial sheaf on this point. Okay.
That's one more
Pardon me?
You mentioned Dobrovolska's result earlier about the
Yes.
cluster structure on the
Non-quantized algebra, yes.
yeah.
Uh-huh.
Is this precisely just the quantum cluster algebra that quantizes?
Yes, yes, certainly, yes.
That's what this AN is.
Yes, yes, it is. Yes, certainly. Okay. So this K theory is the K group of the equivariant derived category of coherent sheaves on the Grassmannian, meaning each coherent sheaf is supported on some finite dimensional Schubert variety. And now this derived category has an interesting T structure, namely the perverse T structure of Безрукавников and Darinkin. Just equivariant perverse sheaves. Okay, and it is characterized by two conditions. So a complex of coherent sheaves lies here. If its restriction to some Schubert variety lives in cohomological degrees less than or equal to negative dimension of this variety over 2. And here it's very important that all the dimensions are even. Well, in fact, there are various connected components, and in some connected components they are all odd, but at least they are of the same parity in each connected component. And also, dually, the co-restriction lives in degrees at least negative dimension of Gr lambda over 2. Okay, and this is an abelian category. And in fact, it's also Noetherian and Artinian, just like with the usual constructible perverse sheaves. So it has a lot of irreducible objects, and they form a basis in the equivariant K theory. Okay, and what are they numbered by? Well, they are numbered by the irreducible vector bundles on GO orbits. Yes. Yes, certainly. Okay, so here lambda is a dominant co-weight of GLN, so it's a signature. Okay, and it also corresponds to some torus fixed point in this orbit, and then we have the stabilizer of this torus fixed point. Maybe it's enough to have it just inside GLN, or maybe GLN-O is also good. And then I consider an irreducible representation V maybe dual of this stabilizer. And it gives rise to irreducible equivariant vector bundle V mu dual on the orbit. And here mu dual again is a collection of integers like this. And this dominance condition means that mu k is these are just integers, not necessarily ordered, but mu k must be bigger than mu k plus 1 if lambda k is equal to lambda k plus 1. Okay. So this is the enumeration of irreducible objects. Okay, first we fix the support, which is a Schubert variety in Grassmannian. Then we fix an irreducible vector bundle, which is given by this datum. And then we extend it somehow to the closure, from the orbit to the orbit closure.
But if lambdas are distinct, then doesn't.
So yeah, for example, if lambdas are all distinct, then this is just a collection of integers, no ordering at all.
Stabilizer torus.
Yes, because stabilizer torus. Okay, and now the theorem due to Ryo Fujita is that under this isomorphism of Cautis and Williams, the dual canonical basis is the IC basis of the equivariant K theory. Okay. And now let me prove it in the remaining 5 minutes. Yes.
I'm a little confused. Just the isomorphism in algebras, didn't you and Symplectic prove that always the K theory Coulomb branches, I mean, the perverse theories were these
Quantum shifted.
yeah.
But this is something absolutely different, because we construct a homomorphism, a surjective homomorphism from quantum shifted algebra to K theory. And here it is an isomorphism from subalgebra of quantum affine algebra into K theory. It's something like dual to what we do. Instead of surjective homomorphism from quantum shift, you get an injective homomorphism into quantum unshifted.
Is it some sort of W algebra type, like a?
Why? I don't. Why?
Probably not then.
I don't know anything about double. Huh?
It's a subquotient of the quantum loop algebra.
This is just a subalgebra, maybe slightly localized, but just a subalgebra by the very construction. But there is also some dual construction which realizes the same thing as a quotient algebra of some shifted quantum affine algebra. But we don't discuss it now. It's something irrelevant at the moment.
And similarly, this isomorphism from the beginning of the talk between this, without quantization, is also, you're saying, unrelated to
To what?
relationship between Zastava and slices.
No, well, how many? Zastava is a slice, so, and is a generalized slice. So it is just this.
Okay.
So it is related. Okay. So now I want to prove this theorem, and to this end we will use a positive part of our Grassmannian. So the whole Grassmannian for GLN is just the moduli space of lattices. Yes.
How
Yes.
does the theorem of Fujita differ from Cautis Canonical? Because they also IC, they also prove something about IC objects in their theorem, or not?
First of all, I think it's Williams, not Kamnitzer.
Sorry.
That's fine, right. But they, as Hirako mentioned, they do prove that under this isomorphism, all the cluster monomials go to IC bases here. But there are many more IC sheaves than just images of cluster monomials. Well, in a sense, it's something like Kazhdan-Lustig cell theory, and what cluster monomials cover is just the lowest cell, but there is much more. See, for n equals 2, there is not much more. Only the equivariant K-theory of point is missed by cluster monomials. But for cell 3, there is more and more and more. So it's some generalization of their theorem, yes. So the Grassmannian itself is more like space of lattices. L in the Laurent polynomials vector space, like this. And here Grassmannian part are those lattices which lie inside the standard one. The positive Grassmannian is the moduli space of lattices okay, and it is the union, disjoint union of connected components, where here the codimension of this lattice is exactly D. For example, the zeroth part consists of just one point, where our lattice coincide with the standard one. Okay, and now, given this connected component, there is a morphism from the quotient stack we're interested in into the nilpotent cone of GLD modulo GLD times C star. Namely, a lattice L goes to the quotient of the standard one modulo L with the operator multiplication by Z. Okay, so this is d-dimensional vector space, and it is explicitly with an nilpotent operator. It is not well defined, but up to conjugation, it is well defined. So there is such a morphism of stacks. And now this morphism of stacks is easily seen to be smooth. So let me call it, say, chi. Now chi is smooth, and hence the pullback of IC sheaves on the nilpotent cone of GLD are IC sheaves on the Grassmannian. Okay, say this is the first thing. Now I also must have mentioned that the nilpotent cone also has this property that all the orbits are even dimensional, and because of this, the notion of perverse coherent sheaves makes sense. Equivariant perverse coherent sheaves make sense for nilpotent cone, and it was studied in Bezrukavnikov's Langland's theory, and we will use it. Now the second part is due to also Cautis Williams. Namely, it says that the IC sheaves on Grassmannian are or maybe their classes, are invariant under certain involution iota Grassmannian. And the same is true for this Bezrukavnikov theory. And this chi star intertwines the two involutions. Okay, and now the third thing is that you take Anderson-Janssen sheaves e.g. mu on the nilpotent cone. Well, there is Springer resolution from the cotangent bundle of flag variety. Now it has the line bundle O of mu for dominant mu, and you just take the push forward. Okay, this is another basis of K theory, of the equivariant K theory of the nilpotent cone. And what I want to say is that the pullback of Anderson-Janssen sheaves, just by the very construction, goes to certain convolutions of line bundles on the minuscule orbit, omega 1. So just what we called P1 something. Okay, and these convolutions, by their definition, exactly form the dual canonical, dual PBW basis. Okay. Just because of this theorem. You see, because the root generators go to these line bundles and their convolutions go to product, so this is exactly the dual PBW basis. Okay, and now this is all easy, but the last part is transcendental due to Bezrukavnikov. So making a connection to Cardinal-Lustig theory for a affine flag variety of GLD. He proved that the transformation matrix from Anderson-Janssen sheaves to irreducible perverse sheaves on nilpotent cone has this positivity property. So I see on nilpotent cone is Anderson-Janssen sheaf, well, say mu plus the sum of Q inverse like this. Okay, this is the positivity property of Bezrukavnikov using all the strength of his theory. And now we just transported via this, and we see that the same positivity property holds in our setting, and this is the last remaining part of the characterization of dual canonical basis. So we're done. So just essentially quote Bezrukavnikov's deep theory. That's it. Thank you very much.